Hello guys, welcome back to physics, high school physics. Here we go. And what are we going to look at today? Well, we're going to have a quick look at one or two things. And we're going to start off with density. No, not. We're going to start off with mass and weight to make sure we know what they are. And then we're going to quickly flick into density and just a couple of minutes on that. And then we're going to dive into forces and we're going to look at Hooke's law, which is springs, and then very quickly adding forces together and just a little bit of circular motion, just a tiny weeny bit. Okay, so this is high school physics. This is like year 10, year 11, grade 10, grade 11. And I'm kind of vaguely following the Cambridge syllabus, which is 0625 is the code for it, but it's kind of vague and it's physics, which it doesn't matter really which syllabus it's from, does it, guys? It's still going to be physics. So let's dive into forces. And what we hope to do today is to be able to understand these various things here. And these include a quick look at springs, Hooke's law, adding forces, friction, air resistance. But we will start off with mass, weight, and density, just to put our heads in the right place. Okay, so I'm just going to flick around here and get to the screen I want to get to, which is going to be this one. Okay, bear with me. So this is our objective for today, to understand springs, Hooke's law. Let's get rid of that cursor. Adding forces, friction, and air resistance. So over here, we're recycling here, guys. So putting paper in its place, exactly. And we're putting this bit of paper in the recycling. In fact, we're reusing before we recycle. So the first thing is this, mass. Okay, now mass is one of those strange things. When we talk about mass, we often confuse it with weight. Okay, so mass used to be the amount of matter, but kind of is it a volume? So we changed it. All right, so recently we've changed the definition of mass. So mass will be, another word for mass is going to be inertia. So if something's got mass, it resists, okay? It resists a change in motion. Basically, guys, if something is rocking along, it doesn't want to stop moving. And if something has stopped moving, it doesn't want to start. And that's called inertia, okay? Inertia. All right, that's what mass is. And of course, we measure it in kilograms. We also use tons and grams, but for SI units, we use kilograms, okay? And guys, don't worry about metric tons or imperial tons, yeah? They're very, very similar in size. There's hardly any difference. So if someone says to you, is that a metric ton or an imperial ton? It doesn't make any difference, okay? Because when we talk about tons, we're talking about 1 ton, 2 tons, 1.1 ton. Guys, it's a big unit and there's no need to split the difference. There's hardly a thing in it, okay? Like just a few kilograms. So don't be sidetracked by tons. Okay, that's mass. What about weight? Well, weight is measured in newtons, isn't it? You know that. Doink. And newtons is a force. Yeah, we measure force in newtons. So weight is a force and it's caused by gravity. So we just say weight is a gravitational force. Easy peasy, is a gravitational force. Job done. Just remember to give it an arrow to show the direction, because it's a vector and a vector has size and direction. And weight is a force and forces are vectors. Mass is something called a scalar. It only has size. but not a direction. Okay, that's pretty neat, guys. And anything else we need to mention? We can just say that weight equals mass times gravity. And don't forget, guys, that's equal to a force, and a force is equal to a mass times an acceleration. And that makes sense because gravity is 9.8 or 10 meters per second squared. And that is an acceleration. So G is equal to A. Bing, 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 ba-doom, ga-doom, all the way through there. G is A. So there you see, guys, all right? It all ties together. And what's our last little thing we're going to do before we start forces? Just quickly mention density. Okay, we give it a symbol rho. Density equals mass over volume. Okay, so it's going to be kilograms over meters cubed. Watch out for these conversions, all right? So this is a Greek letter, R-H-O, rho. It's not a P. A P looks like that. This is rho. It starts from there, goes like this. Okay, rho, not a P. Okay. So density is mass over volume, kilograms per meter cubed. Water has a density of about 1,000 kilograms per meter cubed. But that's the same as 1 gram per centimeter cubed. All right, guys. So you're going to work on these conversions, and you can do that later on when you come to do revision. If something has a density greater than 1,000, it's going to sink in water. If its density is less than 1,000, it'll float. That's how we work out sinking and floating. Okay. Why is it a ship made of steel floats? Because it's hollow and its overall density is less than 1,000 kilograms per meter cubed. All right. And we apply it to all fluids. So the reason a hydrogen balloon or a helium balloon floats in air because its density is less than air, so it floats. Okay, that's why hot air balloon works. Right, easy peasy. That's the end of that. If you wanted to measure the density of a solid or liquid, you just measure its mass and its volume. Yeah, the mass, we can just chuck it onto a scale, a balance, measure it. And the volume of a regular solid, we can measure the sides, multiply them all together, or we can use a displacement can to find the volume if it's like a pebble. Okay, so if you've got something which is an unusual shape, we can put it into a displacement can. You measure the water level to start with, put the object in, the water level goes up, you can say, the volume is that much. Okay, all goes back to Archimedes and the dude running around, jumping out of his bath and then running up and down the streets without his kit on, shouting out he's found it. Okay, you know the story. All right. Liquids, you can just pour them into an object to find its volume, can't you? Okay. And gases, we can use like a syringe to find the volume of a gas. So these things can all be sorted out. Right. Pretty straightforward. Hey, good. And let's go and find our next bit, which is here. Forces. Okay, not horses. I didn't say horses, guys. Forces. Forces. Good. Right. So forces. Forces will change the shape, the size, or the velocity of an object. Okay. Yeah. You know this already. If you're playing sport and somebody bumps into you when you're playing a game, all right, and they bump into you quite hard, maybe they hit you in the face with their elbow, your face changes shape, okay, and its shape, its size changes because it's got a different volume, okay. So we know that, and if someone bumps into you when you're playing your game of sport, then your velocity will change, which means you'll change your direction or you'll change the speed at which you're moving, or possibly both. Okay, so forces measured in newtons will change the shape, size, or velocity of an object. Okay, pretty straightforward. And if you think about it, you know it already. Okay. So what we next do is this. We take our force and we'll apply it to a spring. So here's our little old spring. And if we apply force to it, yes, it's going to get longer. Okay. And the bigger the force, the longer it gets. Okay. Now we call the length extension. So bigger force, bigger extension. Now I could stretch this by putting a big force on it, and then it wouldn't go back to the original shape. So we don't want to do that here, but we could do that in the lab. So what we end up with is this. We end up with springs. And with springs, we can plot a graph of force against extension. Okay. And we would find doink, that we have a line of proportionality, and F is proportional. That is a proportional sign, I know, to X. And X is our extension. Okay. So we have twice the force, twice the extension. Nice and easy. Now, there does come a time up here, guys, when we put more force on, then it isn't a linear relationship. So it only works up to here, where we have the limit of proportionality. Okay, the limit of proportionality. Yeah. So what will happen is we'll start putting more and more force on, and it will no longer be a straight line. It will start to do this. Okay. So this was discovered by Hooke, and so we call it Hooke's law. I know, it's good, isn't it? And what we want to do is get rid of that fish in the middle. Looks a bit like a fish. It's supposed to be a proportional sign. It is supposed to be F is proportional to X, but we want to use an equal sign. F equals something X, K. F equals KX. Okay. Now force is newtons. Extension is in meters. It could be centimeters in your experiments or in your exam, but we should use meters. And K is the spring constant. Let's write that in. K is the spring constant. It's different for every spring. Okay, easy to figure out what it is because you plot the graph, you take the slope. Because F over X is equal to K, and that's equal to the slope or the gradient. Yes, or the gradient. Let's write that in. What's this under here? Guys, what this is, I'm just covering up the writings. We're recycling, we're reusing. So springs, that's it. And this is Hooke's law. Okay. Now, some people say Hooke's law, just to remind them to put the E in. All right. Some people say Hooke's law, but it's pronounced Hooke's law. And if the E is there or not, I don't think people are going to get too excited and take marks off you if you forget to put the E in, but it would be good if you did. All right. So that's pretty straightforward, isn't it, guys? All right. Any questions about that? I can't hear any, but if there is a question, just put it in the chat and then someone will answer it for you, possibly me. Okay, so next little thing is blank piece of paper. This is going very well. Adding forces together. Okay, adding forces is pretty cool. Right, here we go. Adding forces. Guys, you're going to race home with this one. All right, imagine you've got 3 newtons going that way, and then you get another force going that way, which is 2 newtons. I know you're already ahead of me. You add those 2 together, and that gives us 5 newtons. Okay, now you can draw these as little diagrams. Usually when they're drawn, we make the length of the line proportional to the size of the force. So that could be, say, 3 centimeters long. This would be 2 centimeters long. Yeah. And the arrow goes in the middle traditionally, and that would give us a 5 centimeter line. And that looks like a 6 centimeter line over there. So the length of the line is proportional to the size of the force and the direction of the line is the direction of the force. Okay, pretty straightforward, you know. But, I mean, if that was 13, that would be 15, wouldn't it? Okay, now if it's going the other way, if we get 3 newtons going this way, but then we got 2 newtons going the other way, yeah, then obviously that's only going to give us 1 newton in that direction. Right? That's too easy, isn't it? All right. So we can add them together. This is standard. If they were at right angles, it would be pretty cool, guys. Now, if you think about it, if you've got 3 newtons acting up this way and 4 newtons acting this way. So you've got an object here and you've got a rope pulling this way, or a string pulling this way and a string pulling that way. Okay. Our overall force would be this diagonal. So if we construct this, that diagonal is our resultant. Now, a lot of you guys can do your Pythagoras, can't you? By using Pythagoras' theorem, 3 squared plus 4 squared equals this 1 squared, whatever that is. Okay, I'm going to call it R because it's the resultant. Yeah, 3 3s are 9. 4 4s are good, 16. That's going to equal to R squared. Well, that's equal to 25. So R equals the square root of 25, which equals 5 newtons. Okay. Now, on our syllabus, guys, this is standard. Yeah, this could be in thousands, millions, I don't know, hundreds, whatever, but you just add them together. But if they're going to be at right angles, just use Pythagoras' theorem and figure it out. All right, and you can do this. Yeah, you can do this one, guys. All right, so that's adding our forces. All right, so what's the force going to do? It's going to change the size, it's going to change the shape, it's going to change the velocity. Okay, if something is moving at a constant speed in a straight line, if I say that again, if something's moving with a constant speed in a straight line, or it's at rest, then the resultant force on it is 0. If it's at rest, all the forces are balanced. It's just going to stay at rest. And if it's moving in a straight line, a constant speed, then it's just going to carry on moving in a straight line. All the forces are balanced. Okay. So when the forces are balanced, it'll stay at rest or stay moving with a constant velocity. Same speed, same direction. Okay. What's going to cause something to change? Well, usually friction. All right. So friction is a force between 2 surfaces. It impedes the motion and it produces heat. Yeah. And if you don't believe me, then we can do a very quick experiment. Doesn't take long to do this one, guys. And if you want to figure out if friction produces heat or not, you just take your hands and rub them together. Okay. And after a short while, your hands start to get hot because the friction is producing heat and a little bit of sound. Yeah. Don't forget the sound. So that's our friction. It impedes the motion. It produces heat and a little bit of sound. Don't forget air resistance produces heat. When you watch a shooting star, it's a tiny little piece of rock, guys, the size of a pea or a marble, moving through the atmosphere at 7 kilometers a second. And the air resistance is so great, it heats it up and makes a shooting star. It's not a star, it's usually just a little bit of rock. Okay, a tiny, tiny, tiny little piece of rock just burning up due to the air resistance creating heat. Okay, and the next thing, the last thing we're doing now is circular motion, just to get you on track with circular motion, guys. If something is moving in a circle, am I going to attempt to draw a circle? You know it's going to end badly. Okay. If our object is moving in a circle, then what's going to happen? It's going to have, if our object's zipping around here in a circle, okay, the force to make it move in a circle is acting at right angles and is acting towards the center. Okay. If it's moving in a circle, the force is acting inwards. All right. Now, if that's our object and it's moving, if we want it to move in a circle, as it moves along, we have to push it in because it wants to fly off in a straight line, but we've got to keep pushing it in. So to move it in a circle, the force has to go inwards. Yeah, that's why the force is going in. If the force was going out, it wouldn't move in a circle. Oh, makes sense. Okay, so it's called a centripetal force. And it's acting inwards. Now you guys might think it acts outwards because we've got a thing called a centrifuge, but the centrifugal force doesn't exist. And so sometimes in physics you get this weird question, say a rock has been tied to a piece of string. I mean, who on earth ties rocks to pieces of string? There's some weird people out there. Okay, so here's a lovely rock I found down the beach earlier. All right, if our rock's tied to a piece of string, it's moving in a circle. The force is acting inwards because I have to keep pulling it in on this piece of string. I have to pull it in to keep it moving in a circle. Okay, if we cut the string, it'll fly off in a tangent. So the force to keep it moving in a circle is acting in. Okay, it's very difficult to find rocks to attach to a piece of string, guys. And you can see here, I've been helped by this shell which drills holes. Where are we? Drills holes through there. There, look at that. Which means I don't have to drill holes myself. I'm a lazy person, really, guys. I just got some little sea creature to drill a hole for me. Anyhow, there it is, right? Moving in a circle. The force is perpendicular and it's called centripetal force. This will come back to haunt you, all right? Okay, but just stick with this and you won't go wrong. Right, you lovely people. That is it for this little section. All right, we've covered mass, weight, density. Yeah, density is mass over volume. We said the mass is an inertia, which means it doesn't want to start moving, or if it is moving, it doesn't want to stop. Weight is a force due to gravity. Okay, and then we looked at forces. It changes the shape, the size, or the velocity of an object. And then with springs, good old Hooke's law, F is proportional to X up to the limit of proportionality. Okay, and then friction produces heat. Right, I'll see you next time. And I hope that all made sense to you. Thank you, everybody. Right, off we go. Goodbye.